Alrighty, today we are going to be doing 10.3D, which is the comparison test. So yesterday in the 10.3C we did the ratio test. So this is just another test that you can use to determine convergence or divergence of a series. So I just wanted to point that out because in 10.3B we talk about convergence and divergence of a sequence. So that's just a listing of numbers, but now we're going to be adding them up just like we did in 10.3C. So this is all review right here. We know that if we have a geometric series and it's infinite, the important thing is to look at R. And if the absolute value of R is less than 1, then the sum is said to be convergent, and you can find the sum by doing that formula. But if R is greater than or equal to 1, then it's divergent. So that's one, the geometric series. The other one we're going to be looking at, I'm going to kind of skip this real quick, is a p-series. And a p-series is just a power series, so it's n to some power. So what I want you to notice here is that the variable is a base to an exponent. P is the power, and up here in a geometric, the variable is an exponent. So that's a really easy way to tell the difference between a p-series and a geometric series, and you're going to need to know that difference. So let's talk about the p-series. If you have p greater than 1, then it's convergent. Now, that's a little uncomfortable for us because this is the only one that differs from everything we've been doing. Look at, if it's less than 1, it's convergent. So they're opposite for geometric. Notice that the equal to sign always goes with divergent in both of these. So there is that one right there. Okay. Now, there's a special type of p-series where n equals 1. It's called a harmonic series, and that's right here. So I wanted to point this out because we do use this kind of often. If you take the limit of just that sequence, notice there's no sum formula, then these are going smaller and smaller to 0. And in fact, let me show you right here on this post-it. So if you just have a sub n, a sequence is separated by commas. It's just a listing of numbers. You're not adding them up. This is going to converge to 0 as n gets larger. However, if you take the sum of that sequence, it's going to get bigger without bounds, so it's going to diverge. So RP in this particular one, if you look at it, is equal to 1. And this says if you're less than or equal to 1, then you're divergent. Okay, so before we get into the actual comparison test, we're going to practice identifying geometric and p-series because these are the types of sequences that you're going to use for the comparison test. So use the definition of infinite geometric and p-series to determine whether each series is convergent or divergent. So let's start right here. This is an infinite geometric. It's really easy to tell because the n is the variable, so a sub 1 r n, that maybe that's a sub 1. You can always plug in 1 to find out. I don't think it actually is, but that's beside the point. What's important with our infinite geometric is that we find the absolute value of r, and the base is always r. So this is going to be the absolute value of 1/3, which is less than 1. Therefore, the series is convergent. Okay, so we're just identifying these two and then using the definitions to determine if it's convergent or divergent. Okay, B. This one is n is the base. This is a power series or a p series, n to the first power. So we're going to write p series. We don't need to take the absolute value in a p-series because it's not part of the definition up here. So we see that p equals 1 in our case, and just like we did here, this is less than or equal to 1. See how it says that? You're kind of saying which condition doesn't match. Therefore, the series is divergent. Okay, moving on to the next one. This one, n to some power is going to be a p-series. Okay, p equals 4/3. Compare that to 1. So that's what we're going to be doing. And in this case, what is it? It's going to be greater than 1. Therefore, the series is convergent. I think as long as you wrote this, so you need p-series, comparing p to 1, and then convergent for full credit. This one right here, the n is in the exponent, so that's a geometric, and it's infinite geometric. So we have the absolute value of r equals 6/5, which is greater than or equal to 1. Remember that whenever it's divergent, it gets an equal to sign. I'm just going to write divergent. Okay, so keep practicing. There's a couple in here. I'm just going to go through these real fast. P-series, and in fact, you're more than welcome to do this. This one right here is interesting because students are like, I can kind of see that this is infinite geometric because it's raised to the n power, and that's an exponential. But what exactly is r? So we'll get to that one in a second. This one right here, it's clear to see that this is a p-series. And then this one right here, you have n to some power. So this one is actually also a p-series, and I'll show you how to manipulate it so you can actually find out what p is. Okay, so let's go back to this one. P equals 2, up to the top to compare, that's greater than 1, so this is convergent. This one right here, if I want to, I can choose to write this as 3 times 1/2 to the n. So really, this would be 3/1. Why would I want to write it like that? Because now I can then write it like this. So some of these you're going to have to manipulate to figure out what your r is. So look at 1 to the n power is 1. 1 to any power is 1. So that still is equivalent. And all I'm doing is kind of like reverse shower the power to get the n outside there. This lets me see that my r is 1/2 because it's infinite geometric. That is less than 1. So that is convergent. Then we're going to go ahead and do the p-series one down here. P equals 1/2, which is less than or equal to 1. So because this is a p-series, it's opposite. So this one is going to be divergent. And this one's a little tricky. I don't know if you could see this, but n to the 4th, if I want to try and get it in the proper form of a p-series, which is to have a 1 in the numerator, then I am going to have to manipulate that and rewrite this as 1/n to the -4. So we're used to doing the opposite. We're used to taking our negative exponents and make them positive, but there's no rule in math that says you can't go the other way. So in this case, p equals -4, which is less than or equal to 1. Remember, with p-series, there's no absolute value, so therefore this is divergent. Okay, so that is just identifying p-series and infinite geometric series, and we're going to have to do that for the comparison test. So let's go ahead and take a look at the comparison test. Okay, so comparison test, I have some steps up here for you, and we're going to talk about this, but suppose that you have two series right here, a sub n and b sub n, and they have positive terms. So if b sub n is convergent and this sequence is smaller than that sequence, then a sub n will also be convergent. So think about that for a second. That's saying if you have some series that's small and then this one ends up being even smaller, let's say this one is convergent. If this is convergent and this is even smaller than that one, then this one should be convergent as well. Okay, so you're going to need to know that if b sub n ends up being convergent and a sub n is less than b sub n, then you'll also have a sub n convergent. Okay, that only works if a sub n is smaller than b sub n. Conversely, if you have another sequence, let's look at B sub n, and it's big, okay, like it's big, but it's so big that it's divergent, like it's just going to keep going up. So if B sub n is divergent, and when you look at A sub n and B sub n, and this one's even bigger, that's what that tells you right there. If this one's even bigger than this one, and this one was already divergent, and this one's bigger, guess what? That one has to be divergent too. Okay, so it'll make sense when we get to an actual example, but what you need to know is less than goes with convergent and greater than goes with divergent. Now obviously these tests don't always work for every problem that you get to. Sometimes they're inconclusive, but because this is introductory level, the ones that we're giving you are rigged to work out. So you should never get a less than symbol and a divergent. It shouldn't be that way. We're not trying to trick you right now. Okay, we're just trying to introduce you to this. So we're going to go ahead, and if you want, you can copy down those steps. So the first step is to write a formula for A sub n. So that's what I have right here. This is A sub n. So it's pretty cool because I don't need to figure out what A sub n is. So we're doing this a little different format. So I'm just going to write A sub n right there. And this is 2 over n squared plus 4n plus 1. And then right here is going to be B sub n. Now the first step is to write a formula for A sub n. The second step says create B sub n. So we get to create it? Cool. Using the dominant terms. So in 10.3b, we use the highest power of n. In this lesson, we use the whole entire term coefficient and all in the numerator and the denominator. So the dominant term here is 2, and the dominant term here is n squared. And then step 3 is to compare these sequences. So this just, you have to use a little bit of logic. So we've kind of already talked about this. Which sequence is bigger, the left one or the right one? A sub n or B sub n? And this all has to do with fractions. So take a look here. If I plug in some value of n, which you're more than welcome to do, right here what this is saying is this number will be bigger than this one. Why? Because I'm adding more. So this denominator is bigger. What happens when the denominator is bigger? The whole fraction ends up being smaller. So for example, if you had 1/4 and 1/2, this fraction is smaller even though it has a bigger denominator. So in this case, this one is less than this right here. Okay? So we've done steps 1, 2, and 3 right now. And then 4 and 5 are just the technical process that you have to do. You cannot skip this part. So again, let me just say what we're trying to do is we're trying to say, hey, if this sequence right here converges, why do I want to go with converges? Because up top A sub n is less than B sub n, then this one will also converge. So let me give you a little look at this right here. I just like to put some numbers to it. So don't write this down, just look at it. Here's A sub n right here. And if I start plugging in terms and adding them up, this is what I would get. Now it's going to get bigger and bigger, but you can see that decimal's kind of small. What happens when I do 2 over n squared, which is B sub n? Do you see how that number is even bigger? So if I can show that this sequence right here is converging, then this one has to converge too because it's even smaller than this one right here. So we won't put numbers into it unless you absolutely need to, just to check your work. We can do it without that. Once we know A sub n is less than B sub n, we can say convergence right away. That's what we're hoping our outcome is. So the way that you do this is you say consider. So because we're starting with A sub n, mathematically, we have to explain why we're even looking at this other sequence. So we say consider the B sub n sequence, which we can write as 2 over 1 over n squared. Look at that. What is that right there? That's why we just practiced all this. This is a P series where P equals 2, which is greater than 1. So therefore, B sub n is convergent. So we don't have to write because we define B sub n right here. You can even write B sub n here, but you do need all these little guys. And in this space, you can't just write B sub n actually because you need to defend why it's convergent. And this is convergent by the definition of a P-series. So as long as you have this, I'll know why you're saying that's convergent. So if B sub n is convergent, we're using the comparison test to say that A sub n must also be convergent. So therefore, B sub n is convergent, and by the comparison test, so remember we had to do by the ratio test, you have to write this. You could put CT if you want. A sub n is also convergent. So this right here is just standard protocol right here on how to defend your answer using this test. So I put this up here too. So B sub n is convergent. You can even put this, if you like, by definition of a P-series. So you would just end up changing that either by definition of an infinite geometric or by definition of P-series. This sequence converges. And because it's bigger than this one, and the bigger one converges, it only makes sense that the smaller one is going to converge as well. So we say by the comparison test, the smaller one also converges. Okay? Alrighty, let's move on to the next problem. Alrighty, B. So in this particular one, we're going to have to write what A sub n is. So I always like to make my terms that aren't fractions written as a fraction. So we have A sub n, and we're going to compare it to B sub n. We definitely need to know what A sub n is first. So in the numerator, it looks like you're adding 1 each time. So that would be 1n. That's an arithmetic. We've talked about that. But if I plug in 1 would just give me 1. So what do I have to add to it to get to 2? I have to do plus 1. And then in the denominator, what's happening? That's 1 squared. That's 2 squared. That's 3 squared. So what I'm looking at right here is the thing that's varying is the base. So I can write it as n squared. Now, I'm going to create B sub n, which is going to be n over n squared, because those are the dominant terms in the numerator and the denominator, and I am going to simplify this. This is 1 over n. So now we're going to say which one is bigger. I like to compare which one is bigger when they're in the same denominator. Doesn't that make sense? It's how we compare fractions when we have the same denominators. So where do I have more, in the numerator or in the denominator? This fraction has more in the numerator. So if I have more in the numerator, that makes the entire fraction bigger. Remember, if I have more in the denominator, it makes the entire fraction smaller. So this is like that. And we write consider. And we say consider 1 over n. That's B sub n. That's a P-series, just like the one before, where P equals 1, which is less than or equal to 1. Remember, no absolute value on P-series. So by the definition of a P-series, B sub n is divergent. By the comparison test, A sub n is also divergent. So those are just two sentences that you're going to have to memorize right there. So look at that. Doesn't that make sense? If I find that this sequence, or sorry, this series diverges, and it's actually smaller than this one should diverge too because it's even bigger. Okay, makes sense to me. It's a little bit tough, I understand. Okay, let's move on to C. So this one right here, we're going to do A sub n and B sub n. A sub n is nice, it's right there for us. B sub n we're going to create using the dominant terms. So in that case, it's these constants are only the dominant term when they're only the only thing in the numerator. Okay, you guys ready for this? What can we do with this? We can reverse shower the power. Okay, and that's because I want to be able to write it as either an infinite geometric, or an p-series. Okay, so which one's bigger? Since I have more in the numerator up here, this one's going to be bigger. So right away, my head's already going, okay, I should be expecting divergence here. So we're going to consider b sub n. We have to do this because we didn't start with b sub n in the problem, so we're letting people know that we're taking a look at this other sequence first, and we're going to use it to determine convergence or divergence of the one that they actually gave us. So this is 3 over 2 to the n, so of course you have to write that there. In this case, it's infinite geometric because n is the variable. It's in the exponent. So we're going to look at the absolute value of r because that's the important characteristic of infinite geometric, and that's greater than or equal to 1. So by the definition of infinite geometric series, b sub n is divergent. It's kind of easy once you get it down. You can just memorize the pattern. So by the comparison test, make sure you get all these little details in there. A sub n, the series a sub n, is also divergent. Ta-da! Alrighty, last problem, letter D. Wow, that looks intense, but let's break it down so that it's not so intense. So first thing, you have a sub n and you have b sub n. A sub n is given, we don't have to write it, that's sweet. So there's that, and we're going to create b sub n. And the way we're going to create b sub n is we are going to ignore that, but we can't ignore the radical, so we're going to put that. Okay? And now we got some manipulating to do here. So before we do the manipulating, let's compare. Where do I have more, in the numerator of a sub n or the denominator? I have more in the denominator, which makes the overall fraction smaller. So that one, now I'm expecting convergent, convergent. Anytime you have a less than with comparison test, for now, convergent, convergent. Okay, so now I need to manipulate this because I'm going to start with my consider, but I don't know if this is geometric or p-series or what. So I'm going to break this down for you. This is 1 n to the first power over n to the 5/2. So remember, exponential to radical notation, or radical to exponential rather, is power over root. People have power in the top like the numerator, and people roots of a tree are on the bottom. So this is a square root, so that's a 2. And then this is n to 1 minus 5/2, that's property of exponents, which equals n to the 2 over 2 minus 5 over 2, which equals, I'm really breaking this down, some of you can do this a lot faster. And because I can see, since the base is a variable, I know this is going to be a p-series, I'm going to write it in p-series form, like that. Okay, so this comes all the way to here. So now we can just do our math right now. Okay, ready? Consider, and we take our b sub n, make sure we have n equals 1, infinity 1 over n to the 3/2, and we say this is a p-series, and we say that p equals 3 over 2, which is greater than 1, no absolute value, it wouldn't make sense. So by the definition of p-series, our sequence that we just looked at is convergent. And since a sub n is already smaller, in this case the bigger one is convergent than a sub n, logically must also be convergent. And that's it. Celebrate, celebrate. This is the last pre-cal lesson. Woohoo!